Hello everyone, welcome to our discussion on the continuation of the topic partial derivatives. So partial derivatives viewed as rates of change and slopes. So first let us recall that if y is a function of x, then the value of f prime of x of 0 can be interpreted either as the rate of change of y with respect to x at x of 0 or as the slope of the tangent line to the graph of the function f at x sub 0. So partial derivatives have analogous interpretations. So to see that this is so, suppose C1 is the intersection of the surface of the function z equal to f of x and y. So we have here C1, okay, the C1 here, the orange color. With the plane y equal to y sub 0. So plane y equal to y sub 0, the blue one, this color, blue one, this plane colored blue one. And that C2 is the intersection. C2 means this one, alright, the orange color. And C2 is its intersection with the plane x equal to x sub 0. So this is the plane x equal to x sub 0, this color blue plane. Alright, so this is shown in this figure 13.3.1. Thus, the partial derivative of the function with these coordinates at x and y sub 0 can be interpreted as the rate of change of z with respect to x along the curve C1. Okay, so this is our curve C1, right? And fy, or the partial derivative of x sub 0 or y, can be interpreted as the rate of change of z with respect to y along the curve C2. Okay, so this is our curve C2, the orange color. So in particular, the partial derivative of the function with respect to x at this point with coordinates x sub 0 and y sub 0, so meaning at this point, is the rate of change of z with respect to x along the curve C1. Okay, so along the curve C1, this is our C1, curve C1, at this point, right? At this point, x sub with the coordinates x sub 0 and y sub 0. And f, or the partial derivative of the function with respect to y at the same point, okay, looking at this picture here, so at this point x sub 0, y sub 0, meaning the coordinates of this point here, is the rate of change of z with respect to y along the C2 curve, or the curve C2 at this point. Okay, so I hope you have understood what does it mean partial derivatives viewed as rates of change on slopes. All right. So in applied problems, the interpretation of the partial derivative of the function with respect to x at this particular point with the coordinates x sub 0 and y sub 0, and also the partial derivative of the function with respect to y at this specific point with coordinates x sub 0 and y sub 0 must be accompanied by the proper units. We can see at example number 4. So this example here. So recall that the wind chill temperature index is given by this formula. Okay. Then compute the partial derivative of the wind chill temperature index W with respect to V at the point, at this point, with the coordinates T stands for the temperature, and V, which is equal to 25 and 10, and interpret these partial derivatives as the rate of change. All right. So here's the problem again, and the solution to this problem is here's the since we're solving this problem using the partial derivative, so this time we have to uh, take the partial derivative, no, of the given function. So this time we are going to hold t as constant or fixed, and we have to differentiate it with respect to v. So partial derivative of the given function w, the wind chill temperature index, with respect to v at this point with coordinates t and v. So since we hold t as constant, so the first term here, derivative of this, now this is our function. So the derivative of this is a constant, so this is 0. And this is constant multiplied by t, but we consider t as constant or fixed. So the derivative of this is also equal to 0. So that's why we have 0 here. Alright, so what is left is this one. So since this is constant, okay, this is constant, so we have 0.4275 t minus 35.75. So the whole thing here is constant, but this is multiplied by v to the power 0.16. So we have to apply the derivative of constant constant multiple. All right, so we have to use the formula. So the derivative of so we'll just apply this, the derivative of the constant times u, right? Or we may use the other notation. Okay, I'll use the other notation, like the derivative of the constant, okay, with respect to, in this case, we are differentiating partial with respect to v. So you say, so constant times u, so this is equal to constant times the derivative of u with respect to v. So u times with respect to v. So we'll use this formula. So that's why here we have this is constant, okay, because this 0 here correspond to the derivative of this, which is constant, so that's 0. And derivative of t, so this is constant, so the derivative of this is 0. T is also constant multiplied by t is also constant, so the derivative of this is also 0. Okay, so that's why we have here 0. And then this is constant, right, multiplied by v, which has the power equal to 0.16. So applying the power rule here, so we have this. So 0.16 minus 1, that is negative 0.84. All right, so this is the result after our differentiation, partially with respect to v. So since w is in degrees Fahrenheit and v is in miles per hour, so v, sorry, I forgot to mention, v is the uh, velocity, so miles per hour, that is a rate of change of w with respect to v. We'll have a units in terms of degree Fahrenheit per mile per hour, which may also be written as something like this. Okay, you just do the rule in multiplication of fractions here. So substituting t is equal to 25 and v is equal to 10. So this gives us approximately the rate of change approximately equal to negative 0.58 degree Fahrenheit per mile per hour. Now, this is the instantaneous rate of change of W, the wind chill temperature index, with respect to V. So at this certain point, and this is the temperature 25 degree Fahrenheit, then is the miles per hour. So we can conclude that if the air temperature is constant at 25 degree Fahrenheit and the wind speed changes by a small amount from an initial speed of 10 miles per hour, then the ratio of the change in the wind chill index to the change in the wind speed should be about negative 0.58 degree Fahrenheit per mile per hour. Okay, so this is one of the examples as our application to the partial derivatives. Okay, now we can confirm the conclusion of example number 4 by calculating this, okay, using the formula, no, and the limit. So we have the approximate value, so we can use this formula class. So we have function of this, or W 25, this is the temperature, the velocity, plus we have the delta V, the change in velocity, minus this one, then divided by the delta V. So this is the formula, no, in calculating the approximate value. So that is the values for delta V near to 0. Okay, so geometrically, if you refer this to this illustration, so f, the partial derivative of the given function with respect to x, the partial derivative with respect to x at this point, okay, at this point. So this can be, so again, this can be viewed as the slope of the tangent line to the curve C1. Okay, so this is our curve C1 and this is our slope. All right, the line that is passing to this point, that is tangent to this curve C1 with these coordinates. And partial derivative of the function with respect to y at the same point, okay, so referring to this illustration here, can be viewed as the slope of the tangent line to the curve C2. So this is our C2, right, the orange color curve touching this point, okay, tangent to this point. So this is our slope. All right, so we will call this partial derivative of the given function with respect to x at this point, okay, this point or this point, so they're just the same, the slope of the surface in the x direction at x sub 0, y sub 0. So okay, so for this one we call it the okay, so we call it the slope, the surface in the x direction at x with the at coordinates at the point with the coordinates x sub 0, y sub 0. So referring to this, okay, referring to this illustration here. Okay, so we're referring to this slope. And the other one, the partial derivative of the given function with respect to y, the slope, no? This is the slope of the surface in the y direction at this point. So we are now considering this illustration class. So again at this point, but this one is at the y direction. So this is our y direction. All right. This is our y direction. So this one here is the x direction. Okay, so I hope you understand this particular example, how we apply the concept of partial derivatives into this example. Okay, and then we have example number 5 here. Just to expound more about this topic, talking about partial derivative as the rate of change or slope. We have here example number 5. Let the function of x and y equal to x squared y plus 5y cubed. So we are asked here for A to find the slope of the surface of the given function z equal to f of x and y in the direction at the point with the coordinates 1, -2, and B find the slope of the surface z equal to a function of x and y in the y direction at the point with these coordinates 1 and 2. So the other one is at x direction. Okay, at x direction, the other one is at y direction. So same point. Okay, so for our solution here for letter A, so what we're going to do is just differentiate, right? So differentiating the function with respect to x. So we have here the notation, the partial derivative. Okay, so we use this notation to represent a partial derivative of the given function with respect to x. All right, so we're given this function. So we're differentiating partially with respect to x. So it means that we have to hold y as constant. Okay, so our y is constant. So differentiating partially with respect to x, holding y constant. So this is our given equation. So y is constant. So differentiate only this one for the first term. So differentiating x squared using the power rule. So this will go down. So that will become 2x raised to power 1 and times y. So that's why we have here 2xy. Then since y is constant, okay, so y cube is constant, right? Times 5 is a constant. So derivative of this part here is 0. So that's why we have here our first, the partial derivative of the given function is equal to 2xy. Thus, the slope in the x direction. So what we're going to do is just substitute the given point. So the given point. So the first number here, this represents our x sub 0 or x. And this is our y sub 0 or y. Okay? So these are x equal to x sub 0. These are y equal to y sub 0. Then substituting these coordinates or these values to the result of our differentiation, partial differentiation. So we'll get, okay, -4. So 2 times 1 is 2 times -2 equal to -4. That is, z is increasing. So this is the conclusion, class, that z is decreasing z is decreasing at the rate of 4 units per unit increase in x. So that's our conclusion. All right. Then for B, so differentiating the given function with respect to y, so we're going to hold x as constant. Okay, so holding x as constant. Okay, so this time x is constant. So constant. Okay, so I'll just erase this one. So we're always referring to the given function, class. So x is constant, so therefore we have to differentiate this y. Okay. So for our first term, so differentiating this first term with respect to y, so x is constant. So derivative of y with respect to y is equal to 1. 1 times x squared. So that's why we have here for the first term equal to x squared. Then for the second term, so 5 is constant. Then this is, we are differentiating the derivative of this given function, part of the function with respect to y. So we will apply here the power rule. Okay, so applying the power rule here. So derivative of y cube. So what is the derivative of y cube? So derivative of y cube is equal to, using the power rule. Okay, so using the power rule, so this becomes 3y squared, then multiplied by 5, so 3 times 5, 15, 15y squared. So that's why we have here 15y squared. Therefore, so the slope in the y direction, okay, so the slope in the y direction is equal to 61. So substituting the value of x and y. Okay, so once again, this is our x equal to x sub 0, which is equal to 1. And this is our y equal to y sub 0 equal to minus 2. Okay? So I hope you're able to follow, class. Okay, so the slope, therefore, z here, z is increasing. So the other one is decreasing, but for this part of our solution, so our z here is, our z is increasing. So z is increasing at the rate of 61 units per unit increase in y. Okay? So I hope you're able to follow, class, and if you have any question, so you may just message in your message in our group chat, or you may leave your comment below. Thank you very much, and see you again in the continuation of this topic in the next video. Bye.